Welcome to the Explainer. Today, we're going to decode the math universe by looking at its absolute foundational building block, the mathematical function. We're going to take a macro to micro approach here. We'll start with the big picture, the grand landscape of what a function actually is, and then we'll zoom all the way in to look at the exact nitty-gritty mechanics of how these engines work on a graph.
So have you ever wondered how incredibly simple rules can shape the entire math universe? I mean, at its core, mathematics isn't just a bunch of random numbers floating around in the ether, right? It's an elegant, highly structured system. And to really understand how those rules map out our reality, well, we first have to understand functions. Okay, let's dive into this.
Our source material offers this brilliant, almost tactile metaphor that I absolutely love. It says, think of a function like a machine. You put in a value, the machine follows a rule, and you get one result back. It takes this incredibly abstract mathematical idea and completely grounds it. You literally feed something in, the gears turn according to a very specific rule, and boom, a predictable result pops out.
Now, to keep any machine running smoothly, you need raw materials. In math, we call those raw materials the domain. You can think of the domain as the entire set of possible inputs. It's the collection of all the valid numbers you can safely feed into the front of our mathematical machine without, completely breaking it.
And on the other side of that assembly line, we have the range, which is the set of possible outputs. But here is the golden rule of this machine, the absolute defining characteristic that makes a function an actual function. For every piece of raw material you put in, exactly one finished product gets spit out. One input, exactly one output. No exceptions.
But, this factory doesn't just produce one single thing. Let's move to and see how this builds. Because once you establish that basic rule of inputs and outputs, you suddenly open the door to a vast, sprawling universe of functions. And each one has its own unique set of rules and visual behaviors.
The sheer variety here is just incredible. We've got linear functions that generate these perfectly straight lines, quadratic functions with their sweeping U-shaped parabolas, polynomial functions built from powers of x, and exponential functions where the variable itself actually rockets up into the exponent. The source material even points out functions based on behavior, like periodic functions that just naturally repeat after a fixed interval. The major takeaway from all this? The specific mathematical form of the rule completely dictates the physical shape of the graph. It's literally a genetic code for shapes.
If we step briefly into advanced algebra for a second, we can actually peek at the internal wiring and categorize these machines by their mapping behavior. For instance, are they one-to-one or injective, where different inputs always yield different outputs? Are they onto or surjective, meaning they hit every possible output? Maybe they're bijective, doing a bit of both. Or perhaps they're many-one, where multiple inputs awkwardly share the exact same output. It's a really brilliant way to classify them just by tracing how the wires connect.
So the crucial point is, to truly grasp the mechanics of how these functions work visually, we need to focus our spotlight on the real star of the show, the linear function. Written in the classic slope-intercept form as y equals mx plus b, this specific machine is defined by one beautiful, unchanging characteristic, a constant rate of change.
Let's break down the anatomy of this equation, starting with m, the slope. Slope measures exactly how steep a line is, dictating its spatial movement as you read the graph from left to right. In our math machine, you calculate this as the rise over run, literally measuring how far up or down the line travels for every single step it takes to the right. Let's try to visualize this movement. Picture an upward mountain climb. As you move to the right, the line rises. That, right there, is a positive slope. Now picture a downward fall, like you're skiing down that very same mountain. As you move right, the line falls. That is our negative slope. It's great because the simple visual direction on the page instantly tells us what the mathematical rule is doing to our inputs. But what if the line doesn't rise or fall at all? Well, a zero slope means the line is perfectly horizontal, just completely flat across your screen. Now contrast that with an undefined slope, which is a perfectly vertical line. And here is where things get really fascinating. A vertical line actually breaks our golden rule. Think about it. For a single input on the x-axis, it attempts to spit out an infinite number of vertical outputs. Because of that, a graph with an undefined slope isn't a function at all. The machine literally jams.
Okay, so we've got the steepness dialed in with the slope, but where do we actually place this line on the graph? That brings us to b, the y-intercept. This is the value of the function when your input, x, is exactly 0. Think of the y-intercept as our starting anchor point.
It shows precisely where our straight line crosses the vertical y-axis, right at the coordinates 0b.
Now, what's really interesting about this slide is the sheer simplicity of how the source material lays this all out. Every linear function graph is a straight line, and its entire shape and position are determined by just two simple pieces of information, the slope and the intercept. Everything you need to know about the universe of that line is contained right there in that one little equation.
Let's pull this machinery out of the abstract and actually put it into practice with a specific example from the text, graphing the function y equals 2x plus 1. To map this out, we just isolate our components. Looking right at the equation, we can immediately identify our y-intercept as positive 1, and our positive slope as 2.
And this brilliantly illustrates the sheer elegance of the process. Step 1, we drop our starting anchor, plotting the y-intercept at 0, 1. Step 2, we use our slope of 2, which is mathematically 2 over 1, to physically move our point up 2 units and right 1 unit. Step 3, we simply draw a straight line right through them. It's this incredibly satisfying sequence that instantly turns an abstract equation into a tangible visual reality.
We've seen how these inputs and outputs build beautiful, predictable machines that generate perfect lines and curves. But remember, that vertical line, it proved that when the slope becomes undefined, the whole machine breaks down and completely ceases to be a function. So I'll leave you with this thought from the very edges of our source material. If a simple vertical line can break the core definition of a function, what other extreme rules and paradoxes are out there waiting to break the math machine? Thanks for exploring the math universe with me on this explainer, and keep questioning those boundaries.